thank you everyone for joining us. We're going to record this session so we can put it up on YouTube later on in its entirety. But this event is also going to be broadcast, and currently is broadcast, on the Flower YouTube channel. And for those who have seen on the Flower Slack and on the social media, I've also posted this direct link to the webinar if that's the way that you prefer to watch it and participate. This will be, as I mentioned just a few minutes ago, this will be largely an AMA, but one where we've actually provided quite a few scaffolding slides that allow us to explain a number of technical dependencies that relate to this work that we've been doing in Flower and in collaboration with Cambridge towards being able to train large-scale models with GPUs that are physically spread and connected via relatively slow links. So if you go to the next slide, Lorenzo, we can just start to get underway. Just to set the scene, this AMA came about because for about 1 year now, we've been working on developing the raw techniques that are necessary to enable this style of training to be possible. And so again, the style of training means, in this case, being able to train an LLM at relatively large sizes, started at 1.3 billion parameters. We started this work in November of 2023, and by March, we had enabled the pre-training of LLMs up to 1.3 billion parameters in the conditions where nodes, clusters of GPUs were physically distributed across the world. And then that this was really an experimental kind of system in order to observe and identify the core technical problems and then start to address them. Essentially, we wanted to enable this capability. We started to build directly on top of the Flower framework to address the limitations. And starting from November, by March, we had reached 1.3. Lorenzo, if you advance the slide a couple of times. Lorenzo, if you advance the slide one more time. Yeah. And then so by July, we'd reached the ability to do this at 3 billion. And then October, during the Flow seminar series. So that's the seminar series that targets federated learning researchers. We announced that we've managed to scale this to 7 billion. We've trained these models to completion. We've done things like downstream task evaluation. Oh, I think there was a bit of audio feedback, but it's fine. Great. And so the key things that the examples were built with these illustrations of going from 1.3 to 3 billion to now to 7. They've been fully trained, fully evaluated, and with a network of GPUs that are around the world. So locations like Canada, the US, Europe, Asia. So physically distributed, and where the links are relatively slow. And so the fact that we've gotten to this point, we really want to also start to supplement this work by sharing some of the understandings, knowledge we've picked up along the way. Lorenzo, if you just move the slide forward one more. And so all of the work we're talking about in this AMA is represented currently in these 4 technical reports. So I'd invite you to take a look at these and basically look at the different dimensions that are being focused on in each one. If any of this material is sort of really interesting to you, these papers have all the details. And what we're trying to do here is provide the color and also some of the more basic understanding that helps understand these papers better. If you just go forward one more slide. And then, so today, again, we want to make this informal, stream it on YouTube, have a webinar, get questions from the community, where we're trying to make it simpler for other people to do similar things. And importantly, as the space has a lot of interesting challenges to it, by widening, by sharing, basically by sharing our experiences, we hope to have some of these folks come along and start to solve these hard technical problems. But feel free to ask questions at any time. If you go one more slide, Lorenzo. Yeah, feel free to ask questions at any time. You can post the questions in the Slack channel. I'll be monitoring it during the session, and I'll help make sure that the people presenting are aware of the questions at the time. They may decide to answer it a little bit later during the presentation. You can also, if you raise your hand, you'll be invited to speak at some point when we think it's a good time to stop to take that question. Or you can use the Q&A feature of the Zoom webinar. It's pretty good. It just presents the questions you post in order, and we'll just address them asynchronously. Yeah, if you go back one slide, Lorenzo, I think I should have said a little bit more about. So these three folks here are some of the members of the FlowerLLM team that built the Photon system that they're talking about. There are other folks also involved, but we have Preslav, Alex, and Lorenzo, who are going to be sort of diving into different technical facets of the work for you today. So yeah, I think that's everything. Bit of an introduction, and I'm going to hand over, I think, to Lorenzo first.
Cool. Thank you, Nick, for the introduction. Can you hear me well now? Is it okay?
Yeah, I think we can see the slides well.
Cool.
We can hear you well. So it's over to you.
Cool. Perfect. Actually, I will just do the very introduction of this presentation, and then I will leave the stage for Alex, who's going to be the first speaker of today. We just realized that when we started writing these papers and doing this kind of research, it was quite difficult sometimes to explain all the critical aspects of this work and why we are doing this specific type of research. So in this occasion, what we would like to do is conducting the audience and all the people that are interested in this particular topic of research from the very basic details of LLM pre-training to our latest pieces of research, like those that Nick kindly mentioned earlier. To do this, we will touch on some main points that we think are crucial, like for example, how does the LLM pre-training pipeline developed from like some good theoretical understanding of the problems, but also from a lot of empirical results. In particular, what we will put our focus on is large batch training and scaling laws that are so important when developing state-of-the-art models, as well as they were super important to understand what the capabilities of this model were from the beginning. We will have a small introduction on federated optimization, and these will be useful for understanding our Photon system and why federated learning can help in LLM pre-training. In the last part of this discussion, we will put our attention on data heterogeneity, how training data impact the LLM pre-training convergence and pipeline, and what can federated learning tools, so federated learning technologies, do in these situations or to incorporate more coherent information from heterogeneous data sources. So yeah, we won't touch on the very details of every bit involved in the LLM pre-training pipeline, and we hope just to give a sufficient understanding of the crucial points in order to get the most important messages of our research work. So, given this introduction, I'm happy to leave the stage to Alex, who's going to present you the LLM pre-training pipeline. So, please.
Hello, everyone. The honor has fallen on me to present to you the basics of the way that a transformer works. This is necessary for some of the optimizations that we later do. And we should probably begin with the pipeline. This is the pipeline for a decoder-only model specifically, but it is the easiest to explain. Essentially, our goal when we train a large language model is to be able to generate text or predict text. And in this the context of this pipeline, this requires several steps, beginning with natural language text itself, tokenizing it, turning it into a discrete distribution over what we call tokens, and then taking these tokens, embedding them in some dense representations, relating these representations to each other through the transformer blocks using the attention mechanism and the feed-forward networks, and then finally outputting the next token, i.e. generating text. And in order to understand the last step better, you need to know that these models are autoregressive, meaning that we specifically predict the next token, and then for the following prediction, we feed the output of the previous step into the following one. And this essentially allows us to be somewhat data efficient and to train the model on how to correctly continue sentences. To achieve this, we simply take the embedding of the last token at the end of the complete transformer architecture, and we pass it to a linear layer, projecting it to the vocabulary size, turn that into distribution via softmax, and then see what is the most probable token that model would want versus what is the target token that we know is correct based on the training data, and with cross entropy between these two distributions. And this allows us to learn over time how to correctly predict the next token. Now, the transform architecture is not magical. It is an evolution of previous work, primarily RNNs and other methods in the past. The attention mechanism was actually developed for RNNs. Here we can see three types of transformer. The first on the left is the encoder-decoder architecture initially proposed by Attention is All You Need. And this is the full concept in the sense that it has the encoder component whose goal is to make these embeddings within the transformer body as meaningful as possible. And then the decoder's job is to correctly predict the next token. This got split over time for various reasons. At the top, you can see the decoder-only pipeline I mentioned earlier. GPT models and llama models are decoder-only models, and they are highly sample efficient. Below that, you can see the BERT architecture, which is an encoder-only model, which is very effective for understanding complete sentences rather than just predicting the next token, and is widely used for fine-tuning. One thing I should mention is that this presentation is not at all concerned with fine-tuning because we have mostly been focusing on pre-training, but it is definitely a very interesting topic worth exploring. Now, one of the core innovations of the transformer that maybe gets a bit too much attention, but I should focus on it now, is the attention mechanism itself. So the attention mechanism is a way of relating tokens to each other, of figuring out how similar are two token embeddings to one another. And previous methods to determine the relationship between tokens used, for example, recurrent structures, as in you would try to see the token at this position, how does it relate to the next token, whilst building some kind of hidden state to summarize the entire sentence. The attention mechanism is different. It's a quadratic operation, which takes every single token and relates it to every single other token, and uses the similarity of this relationship of these tokens to build an aggregate embedding, which in some sense replaces a given embedding with its context, with the meaning that it has in the entire sentence. In the context of the original development of single-headed attention, this is quite simple for a series of token embeddings referred to as queries and a series of other tokens referred to as keys. We are concerned with how do the queries relate to the keys. And based on this relationship, we can aggregate the values. Then it evolves in this multi-headed attention concept, which is simply taking this single-headed idea and multiplying it several times over, such that you can get different perspectives on the same data. If you have multiple attention heads, so multiple attention mechanisms, each one can have a different projection matrix prior to it, and thus can learn how to observe different aspects of the sequence, such as the relationship of the verb with the subject, for example. And the final compute graph on the right is just a schematic representation of what I just explained. This has an incredible advantage compared to previous methods because it is very parallelizable. And now that we have somewhat of the building blocks of this, we need to consider how would you actually train such a model. Given the fact that current models are huge, on the orders of billions of parameters, we cannot do it in a single accelerator. So we need to consider the entire infrastructure necessary. So the first thing you do need are highly powered, high memory accelerators, which can fit either the complete model or a very significant portion of it. And this requires on the orders of thousands of accelerators. For example, the Llama 3 paper used 16,000. And you need these to be very well connected to each other, because if you want to take stochastic gradient descent and parallelize it across multiple workers, you need to be able to synchronize what the workers are doing. And synchronizing this requires very high bandwidths in excess of 100 gigabytes per second. Finally, to feed this, you need huge data warehouses capable of delivering the correct shards of data to the right location at the right time. And in order to do this at scale, you probably need to build a data scheduler like MAST, as Meta has recently done, which requires you to potentially preemptively move terabytes of data between different data center locations just to be able to service the training of these things. So you can already see there are plenty of bottlenecks in this pipeline and in this infrastructure picture. Now, going into a bit more detail on the distributed training, because it is the part that we address the most directly. The current training paradigm heavily relies on 4D parallelism. 4D parallelism just refers to the way that you split the training of the model across different workers and how you split the training data. The simplest form of parallelism is distributed data parallelism, which is taking the same model, replicating over multiple workers, and then feeding them with different data. Each one of these produces a gradient in and of itself, and then you can simply aggregate the gradients. Other methods are pipeline parallelism, where when you allow different stages of the model execution to happen at the same time, because, for example, the first 3 blocks of the transformer don't need the output of the next 3. Next, you have context parallelism, which is very recent. It's simply splitting the sequence into multiple pieces. This is necessary if you really want to be able to use one of these models for very large contexts. So let's say hundreds of thousands of tokens. Here we have the lemma tree specification, and we can see that they need context parallelism only if they take the sequence like something like 131,000, where the sequence length is the number of tokens that the transformer pays attention to at one given time. Finally, we have tensor parallelism, which requires splitting tensors in memory between workers. These types of parallelism can be applied at different levels. For example, data parallelism is often applied across racks, as in across collections of GPUs, because it requires high bandwidths. But tensor parallelism and pipeline parallelism are usually applied within racks. So in the context of this scheme, we can consider the fact that increasing the amount of parallelism that you use in a standard pre-training context is going to require you to have high bandwidth interconnection between GPU workers, and is going to require you to have high bandwidth within a given rack and across racks. So the way this has evolved over time, it started off with some sort of trivial approaches. The most trivial way of implementing data parallelism is just have a complete model replica across all workers, training on different data samples and then aggregating gradients. Afterwards, as people were kept pushing the size of these models to increasingly exorbitant levels, it was necessary to develop ways of making them capable of fitting within memory. So in this case, the most obvious examples is this sequence of papers from Microsoft DeepSpeed, which has in some sense made training very large models possible today. The first 2 papers on this are 01 and 02. They primarily look at what they call fully sharded data parallelism, which requires splitting the model across multiple workers in order to allow it to fit in memory. So instead of having to keep an entire 400 billion model in VRAM, you only have to keep one shard of this model. And you get linear memory reductions in the number of workers that you have. Then they advanced upon this with zero offload, which is taking parts of this pipeline which are not very critical in terms of throughput and moving them to normal RAM and the CPU, thus freeing up more space for everything else. And finally, zero infinity, which is specifically optimizing the exact layout in memory of everything. And without this sequence of papers, it would have been impossible to train the models that we have today. And this brings us back to the problem of communication, which is central to this entire presentation. Here we can see graphs from the zero infinity papers showing what happens to the efficiency of your training in the sense of arithmetic intensity as you increase the bandwidth of your GPU workers and you consider either the bandwidth available when communicating parameters or gradients, or the bandwidth available when communicating optimizer states, which are also very heavy. And essentially, we can see that at very low bandwidths, it's almost impossible to maintain a good level of efficiency. And you need to go very high for it to be in any way, shape, or form reasonable. Now, if you wanted to take the current paradigm and extend it to something like, let's say, a global training system, or even just training across multiple data centers and not within a single data center, this would be your doom, your bottleneck in the situation. And this is what we're trying to address in our works presented today. Q&A.
I don't see any questions currently. I answered one question from YouTube. I'm looking on Slack now. I don't see anything in the question channel so far. Oh, we have something. The question is, I know Photon is open source. When can I try it out myself? And I would say that it's coming very soon. It's not quite fully integrated into the standard Flower system yet. Photon is built as an experimental extension, and so we'll be letting folks know, pretty soon when it's ready for sort of widespread usage. Although I would also emphasize that the papers provide all details necessary that if somebody wants to take Flower right now and implement these things, it's entirely possible. It's just that we are being a bit cautious before integrating it into the main part of Flower until everything is tested and finalized.
Okay, now in this part of the presentation, what I'd like to put our focus on is all the work related to large batch training and going towards scaling laws for large language models. So why are these important, why these exist, and why we care about them? So first and foremost, large batch training is very important because it's what allows people to take full advantage of several hardware accelerators to train any kind of model that can be highly parallelized by increasing the batch size and then speeding up the training in terms of wall time itself, takes advantage of large batch training in most cases. Why these are so important for large language models? Well, large language models being large, being very compute intensive, and being very demanding in terms of resources, require careful tuning of the batch size and correlated hyperparameters in order to not waste your money and make sure that all the GPUs you're paying for to execute the training are worth it. Why this type of work has been so impactful? Well, they basically paved the way to all the scaling laws paper that became pretty popular in the last 2/3 years. In particular, they are the first to show this very nice equality between like the number of steps and the number of samples you have to see, and these basically it's the building block onto which the scaling laws for losses, for compute, for number of samples, and so on and so forth are built on. Now, of course, all this work that I'm going to present has limitations. It doesn't hold all the time in whatever conditions you want. So it's very important, I think, to know exactly what we're talking about and what are the important bits. Now, first, let me reference the original paper. The title is An Empirical Model on Large Batch Training. It's a work by the OpenAI Dota team back in 2018. This is this is the empirical model. They did a bunch of experiments using several data sets, several tasks, several type of architectures, and training a lot of models. There's a related theoretical, more formal work on the right-hand side of this slide. The notation is pretty heavy, as well as the title. Parallelizing stochastic gradient descent for least square regression, mini batching, averaging, and model misspecification. But I assure you, if you want to take a long dive into into this topic, it's a very good reading. Well, let's move to the model now. So the model is built on top of several assumptions. What we will start with is we want to optimize for some objective functions, usually called loss. These objective function can be estimated using training data and the model parameters. Whenever we sample data from a big data set and we're not computing the full the loss over the full data set, we're doing what is usually called batched SGD, mini batch SGD. Well, this is when we're computing also the gradient and we're applying them. So when you're not computing the entire loss over the full data set, we're just batching our data and computing the loss over batches, okay? Now, why is this useful? This is useful because if we want to compute gradients and apply the backpropagation algorithm, using batches allow us to do fewer computations in order to obtain an update for our model. So this is usually the case for mini batch SGD. And if we divide our full data set into single smaller batches, we get an estimate of the full gradient of the model given this objective function. And this, of course, must be averaged over the size of the batch size. Now, what's the point of this estimate of the gradient is that we hope that increasing the batch size, this estimate of the gradient will resemble more and more closely the true gradient over the entire data set. Now, the questions that these guys are trying to answer is, when is that increasing the batch size doesn't provide any benefits to our understanding of the full data set, but most importantly, to our convergence curve. So how quickly we get to the optimum that we're looking for. Now, the way they try to tackle this problem, they propose this model. This model is based on an expansion of the loss displacement of the model over the loss function up to the second order using a Taylor expansion, and substituting this V with the estimate of the gradients, what we get is basically the expected value of this delta in the loss. So what we're gonna not the delta in the loss, but the new loss that we're gonna get given the delta in the parameters. Now, why is this important? Because what we want to understand is what's the optimal step that we need to do in this loss landscape in order to get closer to our minimum. Okay, we want the optimum step because the optimum step will be the one that is going to be more fruitful for us from a machine learning perspective, but also is going to be the one that gives us the best understanding of the entire data set. Now, this equation up here in the middle can be minimized for this epsilon value. This optimal epsilon can be obtained in this way, and this is the final formula after the derivation that you can get. And what appears notably are two quantities. One is the batch size, this small b, and another one is this b noise with this different font for b. Now, what is B noise and what is the batch size? Well, the batch size, we already know what it is, right? The B noise instead is a description of the signal to noise ratio that our gradients are given to us. Of course, the full B noise contains also information from the Hessian and the covariance matrix sigma across gradients. And this is because we did the Taylor expansion up to the second order. But most importantly, this B noise lives in the same space of the number of samples that we're going to see, okay? And this is because we are dividing this to the batch size, and this contributes to scale this epsilon max. Epsilon max being the ideal max step that we can take in order to minimize the loss. So if you imagine to be on this iso loss curve in the loss landscape, what's the maximum step that I can take in order not to go out of this cone, basically. Now, this B noise provides very interesting insights on the training speed and on the training time that are qualitatively explained in the plot in the top right. And we can see that at some point in this hyperbolic curve, we increase the compute cost, but we not decrease the training time. And this is because we reach the value of compute, so the global batch size that we're using, because for every GPU that we add, we're basically increasing the number of samples that we can see in the data parallel context, the one that Alex explained earlier. So we can see that our compute is not paying off anymore, which means that we went much over this B noise that provides the best, the optimal step in the loss landscape. In the plot below, instead, we have a more quantitative explanation of what's the influence of this noise scale. As you can see, whenever the ratio here is below some critical value, that is exactly 1. So whenever our batch size has the same or lower value compared to the B noise here, we have a perfect scaling in the steps that we can do in this loss landscape. But from some point on, exactly when this critical value is passed, we have an inefficient scaling in the sense that we are no longer able to benefit from increasing the number of samples that we see to get to the minimum that we want to. Okay. Now, this is the model, and these are the results. Given the fact that this B noise is pretty expensive to compute because of the presence of the Hessian, they tried to do a full comparison only for one of the disks that they tested. Their final objective was to demonstrate that the B simple, so the simpler version that basically assumed that the Hessian is the identity or a multiple of it. So their main objective was first understanding if this B noise that they came up with was sufficiently good, and if the B simple was a sufficient simplification or approximation of what was the B noise representing. Now, the results of the model are several. Mostly they're saying this model works to the extent that it can predict the order of magnitude of this critical batch size, and this is the blue line in the plot. The critical batch size is the empirical value of the batch size that we can set for this specific problem in order to maximize the utility of our parallelization. Additionally, this critical batch size increases by almost 1 order of magnitude during training, which is another important aspect to take into account. This, for example, suggests that maybe fixing the batch size to the same value throughout the entire training is not the best choice. Or most importantly, we need to change the impact of these batches throughout the entire training in order to match their utility. At last, this cheaper B simple, cheaper to compute, is sufficiently predictive compared to this more expensive B noise. Now, sufficiently in the sense that it's in the same order of magnitude. Of course, we can see a clear gap between these 3 lines, which means that they're not exactly overlapping. But given the fluctuations that a B simple has throughout the entire training, the average contribution that these batches have are good enough to give us insights on, to give us the optimal steps or close to optimal steps. Now, some side results to this entire modeling became very interesting in later works. For example, given this entire construction, and given the fact that we define this B noise to be very close to this critical batch size that I was mentioning earlier, we can kind of devise what are the minimum number of steps and the minimum number of examples that we have to see in order to fully train a model for a specific value of the loss. Now, these lines probably are quite familiar to some of you. Basically, on top of this equation, all the discussion about scaling laws was built. And in fact, if you have read like scaling law papers, you may be familiar with these kind of shapes, with this hyperbola, with different values. In this case, p-test is basically the loss, the value of the objective functions that we want to do, that we want to optimize for. Now, this framework is useful then to navigate these trade-offs and understand like data time efficiency trade-offs. So how many steps we need to do, how many examples we need to process in order to achieve some specific value of the loss we're looking for. Now, another interesting insight regards the relationship between this B noise and the temperature of the training. Now, the discussion here is longer because they propose a model for the temperature as well, which I'm not gonna go into. What's the important bit? The important bit is described by these top two, the equation on the top right. And you can see that both the B noise and B simple have a dependency on the batch size itself and on this epsilon that in this case is the learning rate. Okay, so we see that there's there's a direct proportionality to the batch size and inverse proportionality to the learning rate, and this kind of reflects what we were expecting from the plot earlier, right? That these B noise increases by 1 order of magnitude during training. And what you usually do when you train neural network models and you are at the end of the training? Instead of using the same learning rate, maybe you try to decrease it a little bit, right? In order to make steps that are super, super small or much smaller than earlier, in order not to get out from the good minimum Bayesian that you have found, right? This gave some other results, some other discussions, and I'm posting here a very relevant paper published at ICLR 2018, which analyzed don't decay the learning rate, but increase the batch size. That is exactly what the plot before was showing. Now, this model came with a lot of assumption and caveats. They have an entire page discussing this, worth looking at. Some of these are reasonable, some are a little bit stretched, in my opinion, but of course, like free to discuss, like to read them critically yourself. What are these assumption caveats? For example, for local optimization bias, they focus on the short horizon improvements. So they don't, their modeling is discussing just one displacement, right? Like it's not discussing a random walk over the entire loss landscape, is it? Also, they are assuming throughout the modeling that the conditioning to the optimization is perfect. What does it mean perfect? Like, do you remember the Asian that became like the identity metrics? This is basically it. You know, that adaptive optimizers are trying basically to inject different learning rates to different layers of the model. Like this is the effect that they are supposed to have on the optimization. So what they assume here is that the condition to the optimization is perfect or very, very good. Of course, they have some simplification to the noise scale, which we already discussed. There's this dependency to the learning rate and potential learning rate schedulers, which is not trivial to discuss. The Taylor expansion stops at the quadratic approximation, which is fairly reasonable in most cases. Of course, going over the third order might be even more unfeasible than the second order itself. And there's this general concern about generalization. Maybe some of you are familiar with this discussion, but people were usually concerned with the fact that larger batch sizes were providing with the worst generalization performance. But this is kind of out of date, in my opinion. Like nowadays, we know that this is no longer the case, especially if we do a very careful tuning of the hyperparameter when we use a bigger batch size. Now, what I'd like to mention here before moving on, is what are these assumptions and caveats meaning in the context of the LLM pre-training pipeline that we discussed earlier. Now, for example, when the problem is perfectly conditioned, this means that we need to control as much as possible the optimization trajectory. And this is one of the main reasons why ADAMW has been adopted so widely. Because ADAMW has several momenta, vectors, and these are all contributing to controlling better the optimization trajectory. In addition, this is a good impact on the conditioning is very impacted by the learning rate as well. Like if you're familiar with these things, or even if you're not, I'm going to tell you the learning rate for LLM pre-training usually has a warm-up phase and then a cosine decay lasting for one period. Yes, one period. So what's the point of this? Well, the warm-up is meant to allow the model to explore the neighborhood of the loss landscape and provide a better initialization. So this is the only thing that is meant to happen during the warm-up. At the same time, the cosine schedule helps decreasing gradually the learning rate in order to match what we saw earlier in the increasing B noise. So when the B noise increases, because we're getting closer and closer to the optimum, we decrease the learning rate in order to balance these two effects. Other tools or techniques that were put into this LLM pre-training pipeline due to some of these assumptions were, for example, gradient clipping. These were meant to contrast fluctuations over time and contrast potential heterogeneous B noises across layers in the same update, because this is something they assume, but is a little bit stretched, in my opinion. Of course, they also help contrasting updates that are coupled with too high learning rate for some periods of at some steps of the optimization itself. Other things that are more related to how well behaved is this estimate of the gradient compared to the full gradient, the full LDL gradient that we can compute on the data set, are related to the way samples are batches sampled and are composed. Yeah, and also it's one of the reasons why it's very difficult to investigate. Usually it's very difficult to investigate model capacity and the amount of relevant information in this in LLM pre-training datasets. Now, after this paper, many followed more along the lines of the scaling laws. Why this? Because they were very useful for understanding what it's possible to do, what we can do by increasing the compute or increasing the model size or increasing the size of the data set. So there was a lot of interest on predicting what are the gains of increasing the scale of one of the components involved in the LLM pre-training. Now, from the first one from OpenAI, many came afterwards until like compute optimal, chinchilla models, beyond chinchilla optimal, accounting for inference as well. And this is one of the latest that describes the problem of learning rate schedules and how to do this investigation without a fixed duration of the training. Now, very, very briefly about the scaling law paper, the first one list that gives you sufficient context to understand the others if you want to read them. What they wanted to do is understand for different regimes of this training, different regimes defined by number of parameter, amount of training data, and amount of compute, and potentially the batch size. They wanted to understand how the loss changes when we vary these quantities, and what in these regimes, depending on the regimes, what do we care about when we can, most importantly, increase the compute. When we increase the compute, do we care more about increasing the number of parameters of the model or increasing the number of steps we can do with a given model? The outcome is pretty insightful because the authors basically say that you should always prefer the number of model parameters instead of the amount of data. They give like a tour evaluation, several models have been trained. But of course, like research is going on, and new papers are addressing small problems of these or earlier ones, correcting some of the assumptions or some parts of the modeling themselves. These are some plots that are basically describing what I was mentioning. So on the left-hand side, we have this pictorial description of what we should scale when we have more compute. And this is pretty clear with colors and sizes that we should care about the model size instead of data. And also on the top three plots are showing that the empirically obtained, empirically fitted scaling laws for compute dataset size and parameters versus the test loss. So the metric of evaluation they chose to use. Importantly, another aspect they tried to evaluate was how much the architecture itself of this kind of model matters. The main outcome is that it doesn't matter that much, even though you can see that these curves at the bottom are not completely flat. It's not like whatever the value of the feed-forward ratio is, I'm gonna get exactly the same loss. Okay, so there is some variability, but the best loss that you can achieve has a pretty broad plateau. So you can probably use very different values in a well-defined range and still benefit from the model, from the number of parameters that you increase. Okay, these are some of the limitations of this first scaling law paper. Some of them are mentioned by the authors themselves. Others were kind of investigated by follow-up works. Yeah, for example, to me, the most interesting one is that related to the learning rate schedule. They had to choose training in several models requires you for several durations, requires you to decide the schedule in advance. They found a good heuristics to work this out, but they realized that for models that are bigger or equal actually than 10 to the 10, right? It was 10 to the 8. It's fine. It's okay. At some point, that for some model sizes on, this doesn't hold anymore. So even though they had a relation, this relation was not sufficient to describe even bigger models. Now, before closing this this part of the presentation, I want to mention a few more details, like very, very rough details regarding these three very interesting papers. They are basically continuing the process of coming up with scaling laws or improve the scaling laws or improve the modeling behind them. This first one, for example, that describes the chinchilla optimum on your left, was very influential because it has a very thorough assessment framework. They use 3 different approaches to investigate one hypothesis, and they demonstrated that all these three approaches are pointing into the same direction. And when this is the case, you kind of have very robust results, right? And they changed a little bit the scaling law. So all the coefficients that I showed you in the tables before were changed a little bit by this chinchilla optimum. The main outcome is they increase when you have more compute. You shouldn't skew too much towards the number of model parameters compared to the amount of data you're training on, but you should scale them. You should scale them equally. So if you double the number of parameters, you should double the amount of training data as well. The central work instead takes a very practical point of view. That is, look, pre-training is not the only thing that happens to these large language models, right? Large language models are then fine-tuned for domain-specific kind of tasks or for downstream tasks. And we care a lot about the cost of inference. Actually, the cost of inference is the predominant one in the life cycle of LLMs. So if we take this into account, in order to make our models profitable, we may need to train them longer so that they reach a much better understanding of the language modeling, and they are much easier to use during inference. The last work I want to mention is this describing how we should change the framework of scaling laws if we decide not to fix the duration of the training. This was a big limitation, as I said earlier, because of the cosine schedule. The cosine schedule must have a fixed period that we set in advance. So if we want to train some large language model, we decide the size, we decide the amount of data, we decide in advance how many steps we want to do. And this gives you the schedule that you need to set for the learning rate. Now, if you change the schedule, it's too long, too short, and so on and so forth. The Chinchilla paper gives you a lot of insights on this. You risk too much. What does it mean? You risk either not to reach the minimum that you want to obtain, or worse, you risk model divergence, because at some point the learning rate is too high and your bin noise is too high as well. So you're basically putting your gradient updates are too big. You're over the epsilon max I was mentioning earlier. So you're over that value that allows you to stay at least with the same loss or smaller. And this is quite frequent. Model divergence is a big problem, actually. So how do we account for this? How do we do things without a fixed duration? And they propose a very good solution that is based on fixed learning rates and cooldowns. So yeah, with this, I conclude this part. And I'm happy to take any questions before going on the federated optimization side of things.
We have a few questions, Lorenzo. So let me just see. On the YouTube, we have a question. And perhaps this is a bit premature, but the question is, what are the tools used to train this? I guess by this they mean Photon and FlowerLLM models. What are the tools used to train this alongside Flower and DeepSpeed? Did you use native PyTorch to implement tensor pipeline parallelism? Do you want to take this question now or later?
I think it's okay to take it now.
Okay.
I think the most predominant tools we've been using was PyTorch and some libraries that we're building on top of that. So yeah, it's very difficult since we were focusing mostly on the distributed part of things, the communication efficient part of things, the federated learning part of things. we didn't spend too much time in digging deep into the PyTorch implementation of tensor parallelism or data parallelism or pipeline parallelism, because we were interested in other things. So yeah, I think the most important tool was PyTorch, and I don't think I'd like to mention any more tools, or is there something else we should? I don't think so.
We thank the DeepSpeed team for inventing all of it.
Yeah, DeepSpeed team deserves a lot of credit for many things, especially the heuristics they have. DeepSpeed has a nice auto-tuner tooling that is based on heuristics and basically tells you what's the best configuration that you can have given all the 0 steps that they have proposed throughout the years. And I think that's quite good and worth looking at.
Okay, yeah, I think that's enough detail. Another question we have is, can we create a pre-trained LLM using federated learning to compete meaningfully with models like Llama or QWen? I think the short answer is definitely, just not yet. But Lorenzo, do you want to add more color to that answer?
Sure. Then, like, I would say yes. I think the only part we may want to care about and we may want to discuss and investigate more is related to the hyperparameter side of things. Okay, now we kind of have a quite complete overview of what pre-training LLM looks like and what are all the small things involved, small but with a big impact hyperparameters involved. A reasonable question that we've been asked ourselves these days is, now we don't care just about the compute efficiency, communication efficiency part of things that we will discuss in detail maybe later, definitely. But now it's maybe time to look at how good the model can be. And there's no reason why federated pre-training should provide worse model. Actually, there are reasons from the literature, so theoretical and not yet empirically verified things that are telling us maybe the federated way can provide even better models. But this is, no numbers are out yet.
Yeah, I mean, we're still working on empirical evidence of that. But yeah, so I guess, but the question is, can these methods scale up to things like Llama and QWen? And there's no reason they can't. We've seen no indications that we can't get there. So another question we have is from Demetrius, actually. He's asking, would adding some regularization help to reduce the effect of B noise with respect to convergence? Maybe achieve a better batch size / beta noise ratio?
The answer is yes. Of course, like in most of these cases, there's a trade-off between like the complexity of the method that you use to solve a particular problem and its utility. I think a very good part of the empirical model for algebra training is exactly this one. So they say, look, we have this model. This model is a bit rough to some extent because this B noise uses the edge, takes a lot of assumption, but in the end, it's very expensive because the B noise uses the Hessian and so on and so forth. And they demonstrate that the B simple, the one like super simple to compute, very straightforward, that doesn't require too much computation, in the end is very effective. So a regularization term, yes, it can definitely help, but it must be simple to some extent. So the integration with the entire pipeline must not inject additional overheads. But I know that Alex has a further answer.
I would like to add that in the case of LLM pre-training, we have a lot of these. So first, we clip gradients all the time to a norm of 1 usually, or even less. We use Adam W locally, which is supposed to make the training well conditioned. Every single part of the transformer architecture has been optimized for stability to some extent. And we also use warm-up phases for the learning rate initially to be able to use much higher learning rates. and a series of other tricks well beyond these. So it's always possible to improve the convergence via regularization, and it's done heavily. And federated learning can potentially help as well. We have some early results showing that model averaging, in the case of federated learning, will help stabilize the model with respect to like higher learning rates, which essentially results in you being able to converge more effectively for some hyperparameters.
Great, great. Well, I think those are the questions we've got so far. Those are awesome answers, is what we're doing the AMA for. Let's progress.
Good. So it's up to Preslav now. So now what we'll be talking about is federated optimization. So we can build a bridge between what I've discussed so far and what is our latest research. And thanks to Preslav, we will look at this specific topic.
Okay, hello everyone. Before I start, I'm just going to ask real quick if everyone can hear me well. So Nick, can you give me an affirmative?
Yeah, sounds great. Great microphone.
Perfect. Thank you, everyone. So I would like to extend my welcome to all of you. My name is Preslav. I'm one of the PhD students at the CaMLSys group in Cambridge. And today I'll be talking to you about federated optimization. So as my colleagues alluded to previously, currently training large language models is a very resource-intensive operation that faces lots of bottlenecks. And one of the biggest bottlenecks is communication across devices. So as we saw, having low bandwidth basically means that we can utilize our hardware at a very, very low rate. So what we're looking at is federated learning as a method that can mitigate those bandwidth limitations. So many of you listening online probably know what federated learning is. Many of you probably don't. So I'm going to give you an overview of what federated optimization is and how you can frame it in several different ways. So to begin with, I've put on screen a very simple but very useful diagram on how a federated system looks like. You can see that we have a series of clients, a potentially unlimited number of clients, that all communicate with a central server. Each client owns its own data and keeps it private. This is one of the ways that federated learning has gotten ground in industry to begin with, is through its privacy-preserving properties. So each client owns its own data and does not share it with anyone else. What the client does, though, is it optimizes locally on its data, and then it sends those parameters to a server. The server gathers all parameters and then aggregates those together into a new parameter set that we call the global parameter set. So federated learning is a method that, just like many other methods, developed empirically. So before there was a very deep understanding of the theory, people were doing distributed optimizations in a federated way without really understanding kind of the full depth of the system here. So in this presentation, we've skipped over a lot of the history, and we're directly going into kind of the best current understanding that we have of federated learning. And that algorithm that performs federated learning in our kind of best way is called FedOpt. So FedOpt is a way to formalize federated learning. It has two main parts that I will highlight briefly. So one of the parts is called client opt, or client optimization, and the other one is server optimization. Client optimization is essentially centralized training. How can we train our model locally on a device? And that is restrained by all of the kind of bottlenecks that Alex talked about in the very beginning of this lecture. Now, client opt is not centralized training, however, because it can use parameters, extra parameters given by the server that have been aggregated. Those parameters, however, do not break data privacy, just to make that clear. The second part is server opt. So server opt, or server optimization, uses all of the parameters that we receive from several clients and aggregates them in some way. Originally, kind of the genesis of federated learning was just using simple averaging. So you take all of the parameters and you average them. Later on, in the paper titled FedOpt, it was shown that federated averaging is actually the federated equivalent of stochastic gradient descent performed globally. So with that discovery, many other dynamic methods that use momentum, for example, like ADAM, have been extended to the federated global environment. So I'll give you a brief overview of how those separate things work in slightly more detail. So first and foremost, as I said, we have client optimization. And the way client optimization works is each client has their own personal data. That personal data leads to a loss, and that loss gives us gradients. Using those gradients, we can then produce a new parameter set. There are several methods that we can use. We can use stochastic gradient descent, ADAM, or RMS prop. And because I said that client opt is different to just centralized training, we do have those extra metrics coming from the server, which allows us to perform learning rate schedules or affect kind of the process in any way. So on screen, I've put a little QR code showing a YouTube video, which clearly kind of demonstrates the differences between the different local optimizers one can use. These are pretty, let's say, standard approaches in machine learning. But again, I think it's useful to see the differences between different momenta or just using stochastic methods that don't have momenta. So if this is the case with client optimization, how does this work on the server? So on the server, obviously, we have no data. And when we don't have any data, we don't have any corresponding loss. So how do we get gradients to perform this? Well, the answer is pseudo-gradients, and that's the discovery from the FedOpt paper. So pseudo-gradients themselves are simply the difference of the previous global parameter set and the average aggregation of all gradients that come over from the different clients. Once we have this understanding of what a pseudo-gradient is, we can apply stochastic gradient descent globally on the federated model, as shown here. And when we substitute the equations, we end up with the equation on the bottom line, which essentially is federated averaging. So we can see here the equivalency between federated averaging and stochastic gradient descent when performing this kind of global optimization. You can use the same approach with many other local optimizers, as I said, just like ADAM, or if you want, you can use something like Nesterov momentum to make this server opt algorithm work. And now, once we have this kind of basic understanding of what federated learning is, we can look at different ways we can formalize federated learning problems. So I've given the three ways that you can do this. And first, we're looking at ERM, or empirical risk minimization. So the idea there is that each client has its own local loss function that I've here termed Fi. So this is small f. This local loss function takes the parameters theta and a sampling of the local data distribution xi. So if we take all of the local losses and we scale them based on the size of the data set, we get our local objective function. If we aggregate all of the objective functions together, and again scale them based on the size of the data set at each client, we get essentially the same equation as what empirical risk minimization is. Therefore, solving the federated learning problem is the same as solving empirical risk minimization. So finding the optimal parameter set gives us a set that, again, minimizes the risk over the entirety of the known data. So this is a very useful property. We can reframe federated learning in two more ways. We can look at this as a multitask problem, where we see that each client's data is treated as an individual task. And what happens there is that we have our local loss function, just like we do with empirical risk minimization, but we have this extra term phi that takes all of the local models across our federated population. And this phi acts as a regularization term that captures the different relationships between clients. Now, considering that the data is the only thing that's different in this particular kind of setting, it also captures the relationships between the data sets across devices. Finally, we'll be looking at meta-learning, so federated learning framed as a meta-learner. And there we look at each client as a distinct task. So there, we're aiming to develop an algorithm that helps us to generalize better to new tasks as they come in. So in this case, if we have new clients joining with new unseen data, we're hoping to have a method that generalizes to those quite well. And this generalization is expressed in our function GI, which is some sort of function which takes parameters and then gives us model parameters which are highly optimized. The meta-learning properties of federated learning are some of the things that we hope to exploit in our future work to make federated models better than their centralized equivalents, especially when it comes to generalization. And that is the end of our federated learning introduction. Thank you so much for listening, and I'm happy to answer any questions.
Great job. We've got a few questions on the Slack, actually, that I missed. So apologies to those on the Slack who asked questions before. The questions are as follows. Let's see. Christopher is asking, he's saying, my background is in vision. Are the principles that were used for Photon applicable to VIT models? Oh, I think I also see that Alex has answered this. But how about we do a verbal answer too online for those who have a similar question? Can VIT work with this stuff?
Most likely one can apply the same methods in Photon to visual transformers. We've not done this in our lab directly, but I'm sure that the general methodology of empirical risk minimization applies to those problems as well.
Yeah, I see no reason why it won't work. So someone out there should do it, or we'll do it at some point. Let's see. Another question. I'll just read the question as stated. It says, maybe you'll touch this in the federated optimization section. So you reference loosely the local SGD paper. Don't use large batch, but use local SGD by saying that you can, in fact, use larger batch sizes without loss of model quality. But there's an aspect about the injection of structured stochastic noise with the outer optimization step that was mentioned in the paper and that you referred to in the Photon paper. Could you touch a bit more about why this is useful, where it comes from, and why this benefit becomes more pronounced at scale as you move from 1 billion to 3 billion to 7 billion and so on? There's been some discussion on Slack on this, but I think it's also worth discussing online.
Yes, I can take that. Essentially, we know that the sharpness of the loss minimum matters. And by sharpness, I mean how sensitive is the model's performance or loss, depending on small changes to its parameters. Injecting noise during any training procedure has this effect of perturbing the parameters out of any overly sharp minima and forcing them to generalize better in some sense, because you will get out of these spaces where the loss is very sensitive. In the case of our work, federated averaging essentially serves to increase the noise of the procedure proportional to the number of clients involved in the federation. And we assume that it should work better at larger sizes because we have more parameters and we have, to some extent, less interference from aggregation. It is known that for very large models, they're in some ways better conditioned than small ones. They're highly overparameterized with respect to their data. So the two points are related, but slightly orthogonal.
Cool. I think that's fine. Let me just see if there's any other questions here. Mohammed asked, how do scanning laws adapt to limited data regimes? And can we estimate diminishing returns as data set size grows? Very interesting topic. Who wants to tackle this one?
Were you planning this?
I can take it because I also answered it in Slack. So limited data regimes are very interesting because most of the scaling laws papers are defined with one epoch training in mind. Essentially, to assume you can keep getting more data indefinitely, and your main bottleneck here is how much can you train for, what is your compute budget. And this was true for quite a while, but we have recent projections showing that we will run out of high quality data by maybe 2026, maybe later, and of general data in a decade, assuming that current scaling laws hold. So limited data regimes differ from this because you're most likely going to have to do multiple epochs over the same data or use some kind of data augmentation techniques like artificial data generation, both of which are less explored in the literature. There's recent papers on the topic that find that you can, generally speaking, do multiple epochs or use artificial data to some extent to improve the model's performance, and that you're going to hit diminishing returns a bit later than what we previously believed. If I remember correctly, one of the figures that I read was 2 to 3 epochs are probably not going to hurt. But I would need to find the more recent literature to link it to you in the Slack.
Great. Well, I think we don't have any more questions for this stage. I don't see anything. Yeah.
Perfect. Thank you, everyone, for listening.
So we have is that I guess that starts to wrap it up, right? Correct.
What happened to this one?
Lorenzo,
Okay.
guys.
Let's move on then.
Yep.
So now we will have, oh shit, no. We will have some juice finally. Hopefully. I'm sorry to talk for so long. Hope my voice is not bothering you. Yeah, let's test the awareness of people in the room. Raise your left hand.
Doing the visual cues.
Oh, it worked. It worked.
We
Anyway,
even had
sorry
a
for
couple of
this
guys online. A
now,
couple of guys raised their hands too. So.
We move now to federated pre-training of LLMs. So first thing, where does FL stand, right? Compared to all the fancy distributed parallelism techniques that we've seen earlier. Now I want to build this comparison based on standard distributed data parallelism and cross-silo federated learning. Cross-silo meaning a federated learning setting where all the clients are, in most cases, fully available all the time, possessing, and they are few, so a limited number in the hundreds at most, possessing like good hardware capable of training language models, for example. And I want to compare this with the standard distributed data parallelism because if you look carefully at these two algorithms, there are many similarities. For example, we can assume that our clients are like the workers of distributed data parallelism, and we can assume that the data shards that each of the workers sees in the DDP context is kind of equivalent to what a client has in federated learning. So what are the main differences though? The main differences, in my opinion, are in this like 4 lines between 8 and 11 on the right algorithm compared to what happens at line 8 in the left algorithm. So on the federated learning side, what happens is that we compute the gradients, we apply them, and we compute the gradients again. So we applied several local steps. Of course, this is configured, this is an hyperparameter that we choose, and so on and so forth. For the distributed data parallelism instead, what happens is that for each mini batch that workers see, they compute gradients that get aggregated, usually taking advantage of Ringo reduce, gradient aggregation, or the sort of techniques. And then the aggregated gradient across all the workers is then applied to the model parameters, so that all the workers end up with the same exact version of the model. Now, this is also the origin of the communication efficiency of federated learning, right? Because if we put them on par of the amount of work that they do, federated learning will certainly communicate a number of times less that is dependent on the number of local steps that we perform, okay? So this is the origin of the communication efficiency of federated learning itself. Now, what is like to do federated pre-training? Well, many people have looked into this already. So this is a number of related works that came out, I think, in the last couple of years. They are all based on this main basic piece of like fundamental piece of work from EPFL, from Sebastian Stick specifically, who was the first to give a thorough mathematical formulation of local SGD and why it converges faster, communicating little. From this framework, many others followed in the context of federated learning in general, but specifically for LLMs, all those that you see between the six are tackling a very similar problem to the one that we formulated as well. The two that I like to mention a little bit more are the latest one, the top left one, convergence and distributed adaptive optimization with local updates. This is the mathematical formulation of what we could call local Adam. And in the bottom right, we see this loco DL from KaMLSys. And I think they have a very good drafts, and I think they are under review at this moment, and we will see what comes out. So another question that one may ask is why we would like to change the paradigm of training and move from like the standard centralized procedure to the federated one. Now, as Alex mentioned earlier, the current forms of parallelism require very high bandwidth, so super well-tuned and well-constructed infrastructures. You need to build a data center using high-speed GPUs with high-speed interconnects, RDMA, Rocky, InfiniBand, and so on and so forth. This is very expensive, but also very challenging to do. And if we want in the future to scale up the size of this model or scale up the training itself, we would need probably larger data centers. People are currently discussing about this problem as it's becoming more and more challenging to build data centers anew or to update the infrastructure to the latest technology as the technology comes out. Of course, we are limited. There's an additional limitation that is mentioned here as well. I mean, maybe you're familiar with GPUs and hardware devices of this kind, but there's a new model coming out every couple of years, right? And if you want if you want to produce very quick training pipelines, you may want to use the latest model. But changing and updating all your infrastructure just because of this is becoming pretty challenging. Another aspect of the motivations, because we would like to change the paradigm, is related to fault tolerance. Why do I mention fault tolerance, even though like it was never a problem up to now, right? Well, it's always been a problem, fault tolerance. In particular, because when it happens to train a very big model, it takes a lot of time and also a lot of resources, not just energy, but also like money, financial resources. And if your long training that is supposed to last 1 month stops after 20 days and you waste, I don't know, like several $100,000, whatever, you're probably gonna get mad. This is because you want all the effort that you put into this to pay off, okay? And you don't want to be bottlenecked by several faults or like problems or interruptions that may come naturally. This table comes from the Llama 3 paper as well. And what's interesting about this and what they strongly disseminated after publishing this paper, advertising this paper, is that almost more than 90% of the faults of the interruptions they had during the training were due to hardware. So something that is controllable, yes, to some extent, but still, you buy hardware, you configure it, you place it, you construct the infrastructure, so you can have some responsibility, but sometimes it's just the GPU that is faulty and you have to change it. Now, how does a FEL help in this case? Well, the FEL paradigm, the FEL aggregation, as I showed you in the previous algorithm, is very robust to dropouts, what we call dropouts in the file literature. So whenever a client is not able to complete its task and then just drop out from the current training round, in a standard distributed pipeline, you will need to recompute the contribution that this client had, because if not, your optimization breaks. In the case of federated learning, you will have an impact, but this impact doesn't require training again, but maybe it requires just training for a little bit longer, or training from a different client, or increasing the contribution of some updates. In the end, the handling of such dropouts and faults is going to be much more controlled. I think last piece of motivation is due to data. Alex mentioned this earlier, right? I think you just maybe a little bit this thing here. Yes, you did, right? Okay, I remember correctly. Very good. So what's the matter here? The matter here is that we know, given the scaling laws, given all the discussions that people are having thus far regarding how to make these models, these language models, better and better, we know that they need more and more data. So chinchilla, optimal scaling laws were the first to kind of show that we need to scale the size as well as the amount of training data to get the benefit in performance. But they're not alone. Like many other people showed similar behaviors, and the community kind of agrees that if you throw more data or more information into these models, they're gonna be better. There's also a lot of interest in constructing well-curated, high-performance training data sets. For example, I don't know if you've heard of FineWeb from Hugging Face. Recently, many small models, small like in the size of the billions, were trained on shards of this, and they demonstrated that just because of the quality of the dataset, they were able to increase the performance by several percent. Now, given this situation, we want to increase the data, but it seems there is going to be a big problem, because open source datasets or public available datasets are not going to be available in the sizes that we would expect to train large language models. This paper from Villalobos et al., Will We Run Out of Data, is showing exactly this trend. And this is pretty concerning, especially because of the deadlines that they give us, like 2027, 2028. They're quite close, right? Even though like this entire environment is progressing quite quickly. How does FL help? Well, FL can tap into private data sources. So basically, it can extend to an entire bucket of untapped data that is available worldwide now, but no one can get access to it. Also, you can solve further problems of copyright or other things. And we have investigated some of these issues in the papers that Nick showed earlier at the beginning of the session. Now, what we proposed with the Photon system that I will discuss in a bit is to execute federated pre-training pipelines of large language models on silos. So on these emerging distributed scenarios that are briefly summarized here. One situation could be that of enabling cross data center collaborations. So we put together parts or like just some GPUs, some instances from different data centers that are distributed worldwide, like one in the UK, one in the US, one in China, why not? And yeah, the broadest, the better, I would say. Of course, we will need federated learning for this scenario because the bandwidth between these data centers, the cross data center bandwidth is very, very limited, and we can't afford to use the standard distributed algorithm. Other than are very interesting in terms of setting is that related to commodity hardware. Maybe some in the audience has some GPUs at home. I don't know. I don't have any actually. I don't know. I'm poor. Yeah. but we do have computing devices, right? Like even my laptop can do some computation. Maybe it can't train like a Llama 3, but it can do something. Can we use this commodity hardware to do federated pre-training of large language models? This is one of the emerging scenarios as well. So what we want to enable with our system is these sort of collaborations. Of course, they have their own peculiarities and limitations and challenges, but in general, we believe that federated learning is currently the only distributed technology that can take advantage of these scenarios. Now, let's come to the Photon system. I will briefly go over the main components. Thanks to DQ for this very nice diagram. So this slide shows the main components of the Photon system. As many other FL systems, we have a server side, the aggregator that is in charge of sampling clients, execute the outer optimization. It may have some GPUs as well in order to do some tasks of evaluation or this sort of things, but most importantly, it orchestrates the training and takes checkpoint frequently, more or less frequently, depending on the setting, in order to make sure that everything is going as it's supposed to go. We also have a communication link between clients and server, and each of the client has several subcomponents. They do have a part that handles the hardware, so how to manage one GPU or multiple GPUs or multiple nodes, depending on the setting. They execute the local pipeline of optimization that is usually AMW optimizer over the entire model or part of it. They do some local checkpointing in order to being more robust to false dropouts and all the problems I mentioned before. And most importantly, they are the connection to the data sources, which can be also decoupled from the clients in our system design. These can be private, they can be public. We allow for a lot of flexibility. The system workflow looks more or less like this. Everything starts from the server that produces the initialization. It's very important for the sake of convergence that all the clients start from the same initialization. So this must be given from the server itself. A sampling step happens in the sense that if our population is very large, but we don't want to tap into all the clients at the same time, we may want to subselect some of them that are available at that moment. To this client, we're going to send the latest model version of the model. They will execute the local training, take the relevant steps to make the procedure robust, and then send back these pseudo-gradient updates, which will be aggregated using an outer optimizer that is fed average for most of our experiments. And this fed average then produces the new version of the model. And this procedure is iterated over. Now, just showing some results of our latest archive paper. Now, what we wanted to understand here is how does the federated training recipe that we propose impact the training time? Now, let's put centralized and federated on par in terms of setting, and we assume they have the same hardware available in the same conditions in terms of connectivity. And as you can see here, while in terms of compute, federated learning requires some more time, some more compute time. In terms of communication, given the very much less frequent communication, and for the federated optimization, in the end, the federated learning in this scenario may take less time to train, less wall time to train the same model. Now, one may ask, what do I need then to use to participate in the federated pre-training? Because I mean, I've heard of people pretty excited to do this thing like at home, or Lorenzo, I have these 3 GPUs. What I can do with them? I mean, you can do things, right? Like, yes, yeah, maybe it's not many people. Anyways, it doesn't matter. So, what do you need to participate? You need GPUs. Yes, you do, because that's kind of How many? Well, it depends. It depends on the model size, right? So depending on how big the model you want to train is, we may want to require bigger GPUs or more GPUs. Of course, you need data as well. Okay, this is very important. If you don't have data, you're not useful to the federated training, right? Like you can't train on nothing. But most importantly, you need a good framework. You need a good framework and a good system. And what about the Flower framework? Yeah, the most popular federated learning framework that we have right now. And why not using it for the system itself? So now in the next step, we will discuss a bit more on training data and heterogeneity and introduce one of our latest works that is having quite some success. And I think it's very interesting. But before letting Alex present all this cool stuff, if you guys have any question from online or in person, we can take them.
I think we're good to go.
Hello again. I'm here to torture you with more building blocks before we can move on to the interesting bits. Yeah, that didn't work as well as I expected. These are not changing.
It's okay. Right now.
Okay, so our next work is going to be concerned with the embedding space of these models. And to get to that point, we need to go over how we obtain these embeddings. So in the case of language models, we have to consider the tokenization procedure first and foremost, which is simply taking a sequence of strings and turning it into a discrete space that we can actually represent with our model, since the space of words is infinite. And the most common ways of doing this are all frequency-based, like byte pair encoding, which is essentially just looking at commonly occurring pairs of bytes and merging those that occur most frequently. And the effectiveness of this is highly reliant on the pre-training corpus. So if you have a pre-training corpus that is only English, this is going to be heavily optimized towards English. And if you have a multilingual pre-training corpus, you better decide how to sample each and every single one of those languages to obtain a good representation for all of them at the same time. And in classical NLP, this mostly just led to either feature-based vectors or other methods of representing the meaning of a given token. For example, here we have the ways that we do embeddings in like earlier works like Word2Vec and Glove, which are not handcrafted, but they're dense representations that are very easily constructed through simple frequency-based procedures. And these sorts of embeddings allow us to determine relationships between tokens, for instance, the similarity or distance between vectorial representations. If you go to embeddings in transformers, this is one way of doing it. We have two types of embeddings. We have trained token embeddings, which are random initialized and represent the meaning of a given token. And then we have positional embeddings, which are meant to encapsulate what that token means at a given position. These are necessary because the attention mechanism of the transformer is fundamentally position invariant. The attention mechanism is quadratic. It does not care about where a given token is in the sequence. So we need to inject that information into the system. There are ways of doing this that use not trained embeddings, but we are looking at the trained version of it. So we have one embedding per position and one embedding per token. And this then leads to some issues if you have data heterogeneity in your natural language corpus. For example, languages, mathematics, code, all of them can vary in terms of character sets, in terms of vocabulary, in terms of syntax and semantics. And these differences cause two issues which are heavily related: negative interference and the curse of multilinguality. Negative interference is just the standard phenomenon multitask learning, where having multiple types of data in your distribution impacts performance on the others negatively. So increasing the number of tasks makes you worse at each independent task. The curse of multilinguality is this problem specifically for languages, and it shows up both at the tokenization level and at the model training level. And this is going to become very relevant in a second. Now, in terms of what sorts of data sources we can use to train an LLM, we have two broad categories. You have multi-domain data. For example, you have code data, internet-based, like broad language data, mathematics, Wikipedia, factual data, etc. And for multilingual data, we have diverse data sets across many families of languages. In this case, you have a clustering based on some meaning, on some embeddings. And essentially, what we would want ideally is to be able to have as good of a representation for every single one of these subsets as possible. But if we ever need to represent them all at once, we have to make trade-offs given the fact that the vocabulary size is finite. And we can only encode a limited number of these tokens. For example, the same token may exist in multiple languages and have completely different meanings. And the same token may mean something completely different in formal mathematics compared to informal Reddit comments. In a federated learning setting, this sort of heterogeneity shows up in clients having different data distributions. So you can imagine a simple example where a federation includes clients across multiple countries. You would expect them to have different data compared to each other, and thus, in an ideal world, should receive a good representation of their data. But in the way that the standard centralized training pipeline works, you would give them the exact same tokenization and the exact same representations, meaning that they are not getting well served. Since if you're using a suboptimal tokenization on a given piece of on a given data set, you are going to get essentially a worse ability to learn from the data. For example, if you have a tokenizer that's bad on English, you're going to end up splitting every single word into almost character level pieces and then try to reconstruct its meaning from extremely long character strings rather than having large pieces of tokenized text. This is where our most recent work comes in, which is called DEPT, Decoupled Embedding Pre-training for Language Models. The core idea is in a federated fashion to separate the embedding process from the transformer itself. We do this in multiple ways, which I'm going to go into detail later. And we want to obtain a model that's as good or better than the version which has global embeddings. The fundamental reason why we started doing this was highly practical, which is I was using multilingual models and observed that the embedding matrices are huge, and I'm not using most of the tokens on some languages, which meant that I was wasting a bunch of memory to just train them. Starting off from the basic, these are representations of DDP versus federated pre-training. DDP is at the top. So in a DDP context, you would take all of your data sources, feed them through a shared tokenizer, and then train on random samples from all of your languages at the same time. In a federated context, if you keep the exact same paradigm as standard training, you would do the same, but you would train on the 2 languages or 3 languages or however many you have separately, and then you would combine the models via parameter averaging. This has an interesting effect. Whilst in the above, you are generally speaking always activating all the model parameters, and so in the below. In the federated case, your embedding matrix is only going to have the tokens that exist in the local data source distribution activated at any point. So if a token does not exist for your English client, you are never going to see it, and you're never going to have it as an input to your embedding matrix. This leads us to these 2 proposed methods. The first of which is a simple optimization of the standard approach, which is if I know that my local vocabulary is restricted, why am I keeping the entire embedding matrix in memory? So what you can do in this case is simply only keep the parts of the vocabulary that you really need. And then when you aggregate, you have to consider which tokens the client has trained and zero pad everything else. And this has sometimes remarkable memory cost reductions because it's going to reduce the amount of memory that you need to keep the model in VRAM, proportional to the reduction in the number of vocabulary parameters. And it also has some other interesting side effects in terms of like the way it restricts what sort of output vocabulary you can have. But for more details on that, you should read the paper. The next method is a kind of a culmination of this sort of idea, which is simply allowing everyone to have a different tokenizer, a different embedding matrix, a different anything else, and your model averaging operates only over the transformer blocks. Now, this has some interesting implications. For example, if you want to have a very good tokenization of both English and Chinese, you now can do it without having to sacrifice description length on either one of the data sets. And beyond that, you now get very good embeddings for each one of these individual, let's say, either languages or domains. Finally, it means that you never have to communicate these embedding matrices, which means that instead of just reducing the communication cost depending on the size of the matrices, you're now completely eliminating them from the equation. In the case of multilingual models, these embedding matrices can be upwards of 80% of the model parameters for small models and 30-ish% for billion scale models. So they're not at all an insignificant cost. Now, in terms of results, first we have the asymptotic memory costs and communication costs on the top left. These should be quite evident from what I've just told you. They mostly come down to eliminating either the communication of a layer or reducing its parameters. Next to the right of this, we have the downstream fine-tuning results, where generally speaking, models trained in this way outperform their centralized counterparts. We believe this is just likely due to the meta-learning effects of federated averaging. If you don't know, federated averaging is completely identical to a well-known meta-learning algorithm named Reptile, which means that it is in some ways meant to learn how to learn. And if you have heterogeneous data distributions, it should make the model better at quickly adapting to new data. Finally, we have some interesting results regarding stability, which also exist for the IID case that we haven't shown earlier with the Photon system. Essentially, we noticed that the aggregation procedure of FedAverage tends to massively reduce the model and activation norms right after the aggregation step, meaning that over a long period of time, when standard training methods will eventually increase quickly in terms of either model norms or activations and diverge, the federated learning acts as this sort of regularizer, which slows down this effect. The model will still eventually blow up, but it may do so much later than it does in a standard pipeline. And that's everything regarding the new paper. Q&A time.
Oh, there's one question on YouTube. We have so many different channels that people can ask questions on. Okay, so the question is GPU necessary for a regression problem? Like we have 5,000 records, which consists of 5 numeric features. Kindly guide me about this. This is from Samir Ahmad. I think it's slightly off topic, but I mean, I think you guys could provide a bit of an answer there. I guess just to rephrase the question, is a GPU necessary for a regression problem? If you have, say, 5,000 records where you have 5 numeric features, any thoughts? I would guess not, but happy to. What's your view, guys?
That's a very special question, I think. We always assume to have GPUs to execute pipelines in ML in general, but I'm quite sure there are many things that we can do without it. In particular, most frameworks nowadays come with a GPU-only implementation that can be used off the shelf. And all the code we've been building upon has the same condition. So it potentially has the GPU-only deployment.
For that scale of problem, I'm willing to bet it would work just fine to use the CPU. And probably Excel can do it. So I think for like these very small scales, you can use your CPU, and you can probably also use federated learning over CPUs if you've got interesting data.
Yeah. Okay. Well then, let's move on. Oh, another question. Oh, okay. There's a question here on the Zoom seminar thingy from Demetrius. He asks, can we safely say that different embeddings across each client act as a natural non-IID setting?
Can you assume it? The way we build the data sets was essentially forcing this to happen because we're using either different languages or different domains. And we tokenize them with the tokenizers trained independently on the data sets, meaning that they almost certainly ended up at slightly different configurations, even for very similar pre-training data. Now, if you were to deploy this in a real setting, one of the questions that may arise is in how many scenarios should you expect clients to have wildly divergent embedding spaces? And I believe that if your setting is countrywide, then it is very likely that's going to happen. Now, of course, you may want to have one embedding per country rather than one embedding per client, but I don't see any reason why this is not a very common case. Another thing that's very important to note is that LLM pre-training is already divided to some extent between like the way we do pre-training on broad language data and pre-training on mathematics and code. Usually model, the pipeline for these is slightly separate with a lot of expert models trained on code and mathematics, which are then combined into the main model via either some kind of parameter averaging or some other form of distillation, which means that in many cases, this would be beneficial even in a centralized context. So if you were to have a separate embedding matrix for these very important tasks. So I do believe that it is quite likely you're going to end up with IID distributions in some, non-IID distributions in some cases.
I think from a more practical point of view, let's assume that two clients have exactly the same data set, like, I don't know, C4 data set, and they use the SPECT method that Alex described earlier. I think we will observe similar effects on the training procedure to those that we observe usually in federated learning when clients have heterogeneous data sources as well. For the simple reason that, yes, I mean, the training procedure is quite well conditioned, as we said earlier, and tries to bring them all towards the minimum pretty directly. But there's still stochasticity, and in the end, the representations that different embedding layers will put into the space of the transformer body representations are probably going to differ a little bit. Now, what's the impact in terms of, in the sense of the data heterogeneity? This is definitely worth looking into, because depending on the impact of this, one may devise further methodologies in order to account for potential harmful effects or to take advantage of potential beneficial effects.
And it's important to note that even in standard centralized settings, you end up with some kind of filtering because of this vocabulary effect. For example, in Llama, they specifically filter out any tokens that are way outside of the distribution of the tokenizer. So any kind of token that's very out of the left field in terms of cross entropy, they just discard because they cannot deal with it effectively. So this is something that you need to address anyways.
So Christopher is asking, can you go over the photon comparison again? I'm not sure which comparison. It might be, there's a few different comparisons. Oh, this is a federated versus centralized wall clock time. So there's there's a table that I believe was here.
So yeah, I don't know exactly what's the question specifically, but I can say again that the comparison we are proposing here is meant to put federated learning and centralized learning on par in terms of resources they can use. So they have been using the same hardware, so the same number of GPUs in the same connection, in the same topology of connectivity. So if GPUs were far away in terms of physical location, but always also in terms of bandwidth, this has a lot of repercussions on the centralized baseline, because it requires very frequent communication, while the federated learning one is pretty robust to this situation, because the training recipe allows us to communicate less frequently. And as a result, while the federated learning is going to take more time in terms of compute, so time that GPU spent doing computation, is going to communicate much, much less compared to centralized learning. And eventually, in the wall time, so the time that we can measure with a clock, federated learning can be much faster.
And Chris has followed up here on Slack asking, are you saying the flops on federated versus centralized are the same?
Flops would be the same if, I mean, without considering the aggregation itself, flops would be the same if the compute time would have been the same, right?
With some context there, the aggregation is a very small amount of computation compared to even one batch of gradient descent. Flops are primarily determined by the number of training tokens you use. In the case of federated, as we point out in the table, we have more compute time, which translates to more flops necessary to reach the same perplexity as centralized. The comms time is the difference, and this gives us the wall clock time. If you're concerned about flops only, that is a very different discussion, and then you need to consider the same setting in terms of communication.
Yes, and the
but
capacities
he's
of the
following up here.
compute are the same. Yes. So this means if you see a longer compute time for federated learning, this just means that the number of sequential steps that the training performs is going to be bigger compared to centralized.
I would like to add one more element here, which is you can end up with quite good utilization locally for federated, as we can tell from the MFU. So that is simply because you don't need to wait for the communication. We can just do it we can just do a gradient descent step locally without communicating.
I think we're at the end, guys. Let's wrap it up. So yeah, thank you very much, Lorenzo, Alex, and Alex. Oh, sorry, Lorenzo, Alex, and Preslav, for going step by step through all the various kind of components that I guess underpin this Photon and related pieces of work. I noticed you went from even just what is attention and transformers, scaling laws, related pieces of work here on distributed training approaches, Photon, even this most recent kind of interesting things you can do with embeddings. Yeah, so I think this makes those papers much more accessible, and we've given people a few kind of interesting kind of points that are not made in the paper at all. So I think we can draw this to a close. So thank you very much for this marathon session of 2 hours, 10 minutes, deep dive. And if anyone has other questions, they can follow up on the Flower Slack. There's a channel dedicated to this topic. And I suppose we will be able to post any links that are on these slides in that channel. There's a lot of various sort of informative papers that have influenced how the work is being done, so they can be put there for people to look at. And if they have other questions, they could just follow up. This recording will be eventually tidied up and posted on YouTube, although its raw form will be there as a live stream, at least until we have edited this version and posted it. So with that, yeah, thanks guys, thanks everyone who attended, thanks everyone who's live in the room, and we'll see you next time. Okay, take care, bye.